So different ways to heat. At this moment, you may be using one of these three methodologies to heat. It would be either gas, electric, or induction. If the heating process is gas, it is conductive. That means, as you can see, you are throwing flames onto the job is rotating, and it's heating through conduction. Again, electrical, same, although you wind the job on top of it, the nichrome wire gets heated, and the heat from the nichrome wire is then conducted onto the job. And to avoid any loss of heat, we will then wrap this on top of this with a layer of ceravol. In induction, it is through induction. So the heat is not actually being conducted, it is produced into the metal directly. The process is flammable. This process is not flammable. Even induction is not flammable. So from environment, health and safety point of view, or shop floor compliances and safety norms, both these processes are much more safer that way. Coil heating pad, in terms of your gas-based heating or even the nichrome wires, the kind of flexibility available on the coil or heating pads is less. So you have a fixed shape along which you can have the flame thrown at, or the nichrome wire wound at, or the pads being placed at. Whereas in induction, you have a flexible coil, so you have the flexibility to wrapping it around any shape the way you like. Surroundings of where the process is being done. So if you were heating like this, the operator couldn't stand around because there's a lot of loss of the heat generated is moving closer towards the operator, and therefore it would be difficult for the operator to stay around there. Similarly, here also, if you didn't wind it with ceravol on top, in the present situation, when this gets hot, the operator cannot put his hand here, it would be hot. In induction, since the heat is going directly into the metal, the coil itself is not at all hot. You could place your hand onto the coil while the induction process is on, but you would not feel hot. Just a caution, I hope you are not wearing any rings or bangles or metallic objects when you are touching the coil. That can heat the metal. Heating type, again, non-contact, and the ones with the nichrome pads are contact type heating. This does produce, if you're doing gas-based or propane-based heating, you will have some kind of a pollution or CO2 or emissions, whereas electrical and induction are non-polluting. Penetration of heat goes from surface to core. Similarly, here also you would heat through conduction from the surface inside to the core. Whereas in the induction, because the magnetic field is being produced directly inside, the heating is pretty much even across the surface. Efficiencies are 40% in gas, 74% in electrical, and about 84% in induction. When I mean efficiency, I mean per kilowatt that you have pumped the power in, 84% or 840 watts would go into the metal directly. Here about 740 would have gone in the electrical, and in gas, only 400 watts worth of heating would have been passed on to the job. Process advantages of induction, as we have seen so far, it's a very clean technology, no pollution, no flames. It's much faster and consistent heating. As the heat is directly induced into the metal, there is no conduction loss. It's a non-skilled process. So once you put it on, press a button, it would heat on its own, repeat the same each and every time. No skill dependency. It's highly efficient, and localized heating is possible. So if you wanted to heat a very small portion of a very large component, you could do that and take it up to your normalizing temperatures or even beyond Curie point. Quick setup, so coil doesn't get hot. You can, the operator can place on and off the coil very comfortably without having to be very worried about hurting himself. Welder can weld while the coil is in place, which is another advantage. So your rotations can happen since it's non-contact. The welder can be welding and your heating is still on, and the heat is not impacting the welder. Economic, because low power consumption reduces your cycle time, your overall setup plus heating time, and it's excellent for preheating. We'll see a lot of examples following through, and it's also pretty much required for the P91 material. How does it work? A block diagram of an induction heating equipment or a controller. You would put a temperature profile that you wanted to achieve. Say, for example, you want a ramp rate of 50 degrees and you want to do about 600 degrees of peak current. So you would set that here on your profiler. You would have an error amplifier, you would have an amplifier, an inverter, and then the sensors. So this is your actual job, the pipe. The spiral thing here is your inductive coil, and it would have a thermocouple or a sensor placed onto the pipe. This feedback would go to the amplifier, and it would check whether your desired temperature has been achieved or not. If it is not, it would amplify and allow more power to be pumped to the job. If it has already reached the rate that you wanted, it would reduce or hold on to it. So this is the kind of feedback. It works very closed loop. You can have a temperature feedback system. You can also work in open loop. Accurate PID control loop, which has been added, gives you a much better control on the temperature profile. For inner loop power control, PI loop has been added. So accuracies are under 10 degrees is the temperature difference between the outer and inner surface. We did do certain experiments in as thick as 250 thick plates and pipes, and we have found that even over a period of time, the temperature difference keeps going down, and is below 10 degrees and smaller components or lower thicknesses, we can achieve a very good temperature gradient. For power control, two-stage loop has been incorporated so that you have a much better control. Inverter loop is in PLL. Chopper control is also available to invert. So a lot of controls in the power electronics side, which would give you accurate temperature profile that you wanted. What do you expect from an induction heating system for pre-weld, post-weld applications? You expect the equipment to be able to cater to most of your production line needs without replacing the coil head. So as somebody was asking, if you had a pipe or a elbow or a nozzle to flange joint, which was say 18 inches today, and tomorrow that was to be about 24 inches, the ease of doing this, both of them without having to change the coil, would be required. It should compensate for your load variation, thickness of pipe, diameter, surface to core temperatures, ease of process setting, wide range of heating profile, and it should consume less power. The Sigma therm, or the ones, the pre-weld, post-weld heat treaters, induction heaters that we are making, are with air-cooled and water-cooled coils. You can decouple coils. That means if you had a larger job, on one job you could have multiple coils. Multiple machines could be used on the same job. More coils can be decoupled. And when I mean decoupled, means you could cover more area, and we will show you some examples of that. And since it's a PLC based robust PID loop, it gives very accurate temperature control profiles. Typical temperature profile required for preheating and post heating is something like this. Before you weld, you want to preheat the job. So you preheat up to 200, 150, 200 degrees. During welding, you have to maintain the interpass under 250 or 300 degrees typically. And then you should have a slow cooling rate or necessary soaking for post heat for some time. Wait, complete your RT, and then you go in for a post heat cycle, which you have a heating rate of 80 to 120 degrees per hour, depending on thickness. Then you have achieved your 760 degrees, and then plus minus 10 degrees is allowed. Hold it there for a period of 2 to 4 hours. We have done some trials where we have held it for as long as 8 hours and 10 hours to ensure proper normalizing and proper heat distribution all across the thickness. Cooling rates are allowed at about 100 to 150 degrees per hour, and below 400 degrees, free cooling or air cooling is allowed. No forced cooling, natural cooling. This is the profile that needs to be achieved, and the same profile can be easily programmed on the equipment. These are some of the examples shown. On preheating, you can see that the thermocouple on the outside, on the inside, the difference is minimalistic, and the temperature range achieved is much faster. Similarly, if you look at this chart here, which was produced during the post-heat cycle, the cycle was completed in 15 hours. You could have a gradual ramp up as you programmed, held the temperature there for a couple of hours, and then a gradual cooling down, and then bringing it to a nominal temperature and letting it